Is my screen visible?
Yes, sir.
Okay, so in the last class, what were we discussing? Have you revised anything?
That was
What were we discussing? Uh, See, this chapter is like organic chemistry is all connected, right? So in organic chemistry, I would request you to please revise. Without the previous concept, you cannot understand the upcoming one, right? So in organic chemistry, it's the only part of the chemistry where you need to learn regularly, right? I can teach you physical chemistry from the scratch, but organic chemistry is like it won't work like that. So tell me honestly, have you revised anything?
sir.
So what were we doing in the last class? Like what topic we were discussing? Okay, tell me. If you have revised, you should know. Tell me, Ali.
Remember, sir.
What?
Don't remember.
See, in the last class, I gave you a brief about the chapter. What is haloalkenes, right? We talked about what are the uses, how to differentiate them, allylic, vinylic, right? Why the chemical reaction are occurring at the first place due to the polarity in the bond, right? Carbon and halogen. Halogen is more electronegative. It is pulling the electron cloud toward itself, due to which carbon is having a partial positive charge. All of these are basic stuff, right?
Sir.
And then we talked about how to prepare haloalkenes. In organic chemistry, the approach that we are going to apply here is first we will talk the basics about that. The name of the chapter is like haloalkenes. We will talk about the basics. Then we will see the methods with which we can prepare haloalkenes, right? The first method is from alcohols. From alcohols, like the starting reagent will be your alcohol, the starting substrate basically, right? You will change your reagents, you will change your reagents, and you will get the same product again and again, just different methods. The substrate is always going to be alcohol, and you will get different products. Sorry, same product of haloalkane basically. We talked about this Lucas reagent test. What is Lucas reagent test? How can you differentiate if I gave you a test tube containing alcohol? How can you differentiate? It is like if it is 1 degree, 2 degree, or 3 degree. How can you differentiate it? I told you in detail.
Yes, sir.
So how are you going to check whether it is 1 degree alcohol, 2 degree alcohol, or 3 degree alcohol?
Sir, for 3 degree alcohol, the milkiness will come instantly, and for 2 degree alcohol, it will take some time. And for 1 degree alcohol, it will take a lot more time. And
Correct.
if it does not come, then we'll have to use heat.
See, the reactivity of alcohols are 3 degree, 2 degree, and 1 degree. Why? We also talked about this because we have basically two types of mechanism. SN1 and SN2 that we are going to discuss in detail as we move ahead with the chapter, right? So I hope you remember this. If I like do this part again, it will take a lot of time and we have to complete this chapter, right? So I would do one thing. I would request you to please go through this again, do the revision. If you are still having doubts, please ask me in the next class. That means tomorrow, right? You should get your doubts clear before the next class, right? Because organic chemistry is all connected. If you are not able to understand one concept, the upcoming one will go over your head. So please try to at least work hard for this chapter, right? The next three will make sense automatically, right? The second method. Now again, let me open my pen again. See, now the second method again. We are going to start with alcohol. Now we are going to change the reagent. Now we are using NaBr plus H2SO4. What is happening here is these NaBr and H2SO4 are basically this. H2SO4 is an acid. What is the basic work of acid? To provide H positive, right?
Sir.
So this H positive, this H2SO4 will just provide the H positive, and they will react with each other and will like become into HBr. You can either write NaBr and H2SO4, or you can write HBr. The reaction is going to follow the same path. So here, what is happening basically? We are adding alcohol in the presence of NaBr plus H2SO4. We are getting our desired thing or desired compound, which is haloalkene. The main motive of the first part of this chapter is to prepare haloalkane by different methods. So we have prepared what? Haloalkane. Is this haloalkane or not?
Yes, sir.
Alkane containing a bromine. Bromine is a halogen, right? The side products are going to be NaHSO4 plus H2O. Now, just general knowledge. All of this will make like the picture will be clear after talking about the mechanism. But for now, just try to understand it, right? Similarly, the concept that we applied for the previous case, 1 degree. See, if here we have NaBr, right? If NaBr is here, it will be in this form or not? Na positive and Br negative, right?
Yes, sir.
This Br negative has a negative charge. It is electron rich. It will try to attack here. Why? Because due to oxygen, it is having a partial positive charge because oxygen is electronegative, right? This
Yes,
negatively
sir.
charged species will be attracted by a site where there is a deficiency of electron, right? So it will attack here and simultaneously it will remove this OH group, right?
Sir.
Now this OH group is removed from our substrate and our Br is what? Attached to it. Now what is this? Haloalkane, the desired product. Is this
Yes, sir.
making sense? If
Yes, sir.
if it is not making sense, be blunt, right? I would request you to please understand side by side. You don't have to be like think like if I am not understanding, there might be some issue. No, no issues. Just try to ask again and again if there's anything that is not making sense. Right?
Yes, sir.
Is this clear or should I go again?
That is clear.
Right. So what is the leaving group? This OH will be removed and
Yes,
this
sir.
NaBr, they will combine with each other and give us NaOH. Now, this NaOH is a strong base. This is a strong base and we always try the leaving group. The leaving group is what? The group which is leaving our substrate. We always try this leaving group to be a weak base. If it is a strong base, it will again attack to our substrate and give us the initial product. So we always try to get a leaving group which is a weak base. This again, I will talk about later in detail. So for now, this reaction won't occur. How will this occur? We have to first convert our OH into a good leaving group. A good leaving group is H2O. Then we will go by the mechanism. This OH group will abstract the H positive, right? Now, try to remember always if a atom is giving its own lone pair. Try to see here. Oxygen has how many lone pairs?
4.
Two lone pairs, right? Four electrons and two lone pairs.
Yes, sir. 2 long. Yes,
Now, this is lone pair and it has some electron density, right?
sir.
Now, what is happening here is H positive. H positive has deficiency of electron
Yes, sir.
because it has a positive charge. So, in chemical reaction, what is happening everywhere is a electron-rich species, electron-rich site will always look for a electron deficient site and it will try to attack there, right? All of this is happening due to stability purposes. So it will try to pick this electron, sorry, pick this H positive. This is donating its own electron pair, right? This lone pair is uh, oxygen's own lone pair, right? Its own lone pair or not.
Yes, sir.
If oxygen is donating its own lone pair, it will bear a positive charge. The positive charge, which was initially on the H hydrogen basically, is transferred into O. Why? Because oxygen tried to help H positive, and in this process, he feared a positive charge. Right? Is this clear? What is happening here?
Yes, sir.
Now, oxygen is one of the most electronegative element, right?
Yes, sir.
Now, on electronegative atoms, a positive charge is highly unstable. You have abstracted electrons from a species which is very electronegative. These atoms, like oxygen, their tendency to hold the electron is very high. You can imagine it like you have like took money from a person who is very greedy, right? Who never wants to share his money. So he will obviously get anxious, right? Or not?
Sir.
He will be unstable basically. So the moment this oxygen atom gains a positive charge, he will instantly try to neutralize it. How? He will do reaction. Suppose in the reaction we have Br negative, right? Br negative.
Yes,
Br
sir.
negative will attack here from the back side, and this oxygen will take these two electrons of a single bond and leave, and it will look like this, H2O. In this reaction, it is feasible because the leaving group is what? The group which has left our substrate is a stable thing, right? It won't attack back, so it is a stable thing. We can abstract our haloalkene, right? I hope this should make a bit like little bit sense because like we haven't talked about the mechanism now. That's why it might be a bit confusing for you, but I hope you know a little bit.
Yes,
Like
sir.
this is kind of 11 VOC. Is this clear?
Yes, sir.
Now, if we are going through 3 degree, we will follow the what carbocation mechanism. A carbocation will be formed. You have to answer me 3 degree, 2 degree, and 1 degree. Out of 3 degree, 2 degree, and 1 degree, which carbocation is the most stable?
Sir, 3 degree.
Why?
Because it has more number of haloalkenes,
No,
more
because you
number
can
of
say,
halogen.
see. This is my. Uh, I hope you are able to differentiate between 1 degree, 2 degree, and 3 degree, right?
Sir.
If I say this, this is my 3 degree carbocation, right? This is my 2 degree carbocation. Why? Because to this carbon, there are directly two carbon attached, right? And this is my simple 3 degree. Sorry, 1 degree, right? Is this clear? Now try to understand. Have you heard about inductive effect? I told you in the last class what are inductive effect hyperconjugation, right? If if
Sir.
if you have very low money and you have only one friend who is trying to help you, you are getting stabilized, but not that much. Here, this CSC group is doing what? This is donating its own electron density through plus I effect, right? It is donating its electron density to the positive charge. Okay.
Sir.
Now here we have two groups and here we have three groups. So ultimately, the most stabilized positive charge is for 3 degree. And you can understand it in terms of hyperconjugation as well. Hyperconjugation is seen or like calculated like this is our main site, carbocation site. To
Sir.
directly attach carbon, this is alpha carbon. And this is also alpha carbon, this is also alpha carbon, right? Three alpha carbons.
Sir.
Is this making sense? Or should I tell me
Sir,
please?
yes.
Now, how many alpha hydrogens are there for case of 3 degree? 9 alpha hydrogen.
Yes, sir.
Here we have six. Here we have only three. So due to hyperconjugation and plus sign inductive effect, our 3 degree carbocation is more stable. Right?
Yes, sir. No,
Is this clear? Or you have doubts?
no, sir, clear.
So this is how this works. For
Sir,
now, for now, hmm,
sir,
please ask.
sir, today can we complete this chapter?
Like it is very hard because like if I like try to skip some parts, it won't make any sense. We won't be able to
Sir,
complete this chapter like by even tomorrow as well.
because tomorrow it will be better if we can do like revision of the four chapters.
Which chapter?
Four chapters. Four chapters.
See, for that we can do one thing. Like I can teach you from the short notes, and where there you have to do the rote memorization stuff more. So it's up to you. Like I know your exam is on Monday, right?
Yes, sir.
So like okay. Mm, see, I will teach you this chapter in details after the exam, right?
Yes, sir.
For now, let us concentrate so that you can score something from this chapter.
Yes, sir.
You have to like learn it, okay?
Yes, sir.
For now. Give me few seconds. Let me see something. See, these are short notes, right? Everything from this chapter will come from this, but you need to like rote memorize it for now, right? So let us start. See, the name of the chapter is this. We have like preparation methods where we are going to use alcohol with different agents. From alcohols, you have six ways. You have six ways with the help of which you can prepare what? What's the main purpose? To prepare haloalkane, right?
Yes, sir.
So we have six methods. You can, all of them will include your alcohol as a starting reagent, and you are changing what? The attacking reagent, right? In
Yes,
the
sir.
first, we have already discussed in detail what is Lucas reagent, and they might ask you the turbidity test one question. You can use this or you can use this. You will have your alcohol, and if you are reacting it with PCl5, if you are reacting it with PCl5, you will get what? RCl. RCl is a haloalkane. Or you can react it with PCl3, PCl3 or PBr3. If you are reacting it with PCl3 or PBr3, again you will get what? Haloalkane. But the catch here is, if you are using PCl3, you will have to start with 3 moles of alcohol, 3 ROH, and you will get 3 moles of haloalkane. Right? With PCl3, what's different? You will start with 3 moles of haloalkane. Sorry, 3 moles of alcohol, and you will get 3 moles of haloalkane. Right?
Yes, sir.
This is very important. Right? This is a name reaction, and this is very important. So try to focus on it more. If you have your ROH and you are reacting it with what?
So CL2.
This, right? What we call it? Thionyl chloride, SOCl2, right? So again, our product is going to be the same, haloalkane, but the side product here are very important. Why? Because the side product are in gaseous form. This is SO2 and this is HCl, right?
Sir.
Why they are beneficial? Suppose you have to prepare something and you are getting side products, so you have to filter them out. But here what is happening? The side products are in gaseous form. They will automatically escape your mixture and will give you only the desired product, which is haloalkane, right? So
Yes,
this is
sir.
our Darton method, right? Darton method is very important, so you should mark it. The mechanism followed here is SN2 mechanism. Backside attack, right? And see, if they have mentioned SOCl2 with pyridine, SOCl2 in presence of pyridine, then you will get the same thing, but the mechanism followed will be SN2. And if they have mentioned only SOCl2, the mechanism is going to be SNI. We will talk about it while we will discuss in deep. For now, you can understand it. If they have mentioned only pyridine, oh sorry, they have mentioned only SOCl2. The mechanism is SNI. If they have mentioned pyridine as well, then the mechanism is going to be SN2. The products in both cases are going to be same. Is this clear?
Sir.
Ask if you have a question.
Sir,
Mhm.
sir, commercially, like, sir, I saw one
This is
question,
a
like,
very
commercially,
this is a very good method to prepare haloalkanes commercial level. Yeah,
yes. Sir,
right.
so, SOCl2, right?
Yes, this is a name reaction, Darson's method. The name of the scientist was Darson, right? And this is a very good method because why? Because the side products are in gaseous form. You don't have to filter them. You will get your product and the side products will automatically evaporate and the mixture will be pure, basically. Right?
Yes, sir. Yes,
Now, the last method is again starting reagent is going to be what?
alcohol.
But now you have changed reagent again. You are using red phosphorus in presence of X2. X2 could be Br2 or I2, and your product will be again haloalkane. Example is like this, right?
Sir.
Now, the second method. These are the methods where you are using alcohol as your starting reagent. Now you can prepare your haloalkane with different reagent as well. Suppose you are using what? Alkanes. Now, your starting reagent is going to be what? A simple alkane, right? You are starting with a simple alkane. What do I mean by this? For example, you are starting with methane. Methane is alkane. Ethane is alkane, right?
Sir.
You are starting with an alkane and you are reacting it with X2. X could be Cl2, Br2 or I2. You are reacting it with halogen in the presence of heat or sunlight. This is very important condition. Then you will get your haloalkane, right?
Yes, sir.
This goes by free radical mechanism, right? Now, if you are reacting methane with Cl2 in presence of sunlight, in actual what happens? You get mixture of product. Suppose this Cl2 is eliminating only one hydrogen for one case, right? It might uh, like substitute two hydrogen, three hydrogen, or it might substitute all the hydrogen. You will get a mixture of product. How can you control it? Suppose if you are taking CH4 in excess, if you are taking CH4 in excess, the main product is going to be your CHCl3, right?
Yes, sir.
And if you are taking Cl2 in excess, your main product is going to be CCl4. So this is how you can form a specific product, right?
Yes, sir.
Now, the next method is from allylic halogenation. What is allylic position? I told you in the first class, right? Allylic position is the position where we have double bond, and to this double bonded carbon, the next carbon. This is allylic position if something is attached to it, right? So
Yes, sir.
the carbon which is directly attached to a double bonded carbon is allylic position, right?
Sir.
Now you can again from allylic substrate, you can form your haloalkane. How? You will simply use NBS. NBS is a reagent, N-bromosuccinamide, or you can use Br to heat, right? try to remember this. Try to remember this. If you are using Br2 heat or sunlight with alkane, you will get haloalkane. If you are using Br2 in presence of heat, you will get haloalkane, but alkylated halogenation. The bromine will be attached to what position? Allylic position, right?
Sir.
This is allylic position. Bromine will come here. Simple, right? Or what you can do here, you did bromination. You can also do chlorination. You can use Cl2 in presence of heat or simply NCS and chlorosuccinamide. In both cases, your chlorine will be attached to the allylic position, right?
Yes, sir.
But 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 if they have given you Br2, but the solvent is what? CS2. This is very important. They might ask you a question from this, right? If they have given you Br2 in presence of CS2, CS2 is a non-polar solvent. If they have given you these conditions, then you will simply add bromine or chlorine like this. Across the double bond, you will add two bromine or chlorine halogen basically, right?
Yes, sir.
For example, suppose I am doing this. This is a benzene, right? Uh, what we are doing? This is our double bond. Double bonds next carbon is this, right?
Sir.
Our halogen will be attached like this, not like this. Yes, okay.
Sir.
If I have this case, this is my double bond to the next position. This is allylic position. Similarly, I can call this allylic position as well. You can either add at the top or at the bottom. These are our haloalkane products. Is this making sense? Is this clear? How we are
Sir.
doing
Yes, sir.
halogenation and allylic position, right?
Yes, sir.
Now, the fourth method is from alkenes or alkynes. Do you remember Markovnikov and anti-Markovnikov addition? Do you remember this is an
Sir,
11th concept?
Markovnikov's rule.
Yes, Markovnikov rules and
Yes, sir.
anti-Markovnikov rules. What is Markovnikov rule?
Sir, Markovnikov's rule say that where there is less number of hydrogen, there the
Good, very good, very good, very good. You know, so anti-Markovnikov is going to be the opposite case, right? So
yes, sir.
try to understand it. If you are having alkenes as your starting reagent, right? And you are reacting them with what? Either HBr or HCl. Then you will get haloalkane. X could be chlorine or bromine. And see, if you are using only HX with no solvent, no additional solvent, then the addition is going to be what? Markovnikov addition. As you mentioned, the halogen or the attacking reagent will go to the carbon which has less number of hydrogens in a double bonded state. We will see the double bonded carbon and we will see this has less number of hydrogen and the halogen will be attached to it. Is this clear?
Yes, sir.
See, uh, most of the questions, right? Most of the question in your exam will follow the Markovnikov addition approach, but there will be variations. And for those variation, you need to understand the carbocation mechanism, and that will take time. So for now, try to remember it as this. If you are having only HCl, only HBr, the halogen will go as per Markovnikov rule, right? Once your exam is over, I hope it goes well. After that, we will talk about it in depth, right? For now, you can understand it as simple Markovnikov rule. Okay.
Sir.
Now, see, if you have used HBr in presence of peroxide, ROOR is peroxide or pyridine, right? Basically, if you are using this, then the addition is going to be anti-Markovnikov addition. If in exam they have given you an alkene as a starting reagent, and they have given you HBr in presence of peroxide, this ROOR or pyridine. Then you will follow anti-Markovnikov rule. Is this clear?
Sir.
Please ask question if you have some doubts. Ask questions. Right?
So if there is only pyridine, then it will be anti-Markovnikov's rule.
Yes. If you have HBr, see, the anti-Markovnikov rule is for only if you have HBr and pyridine. If you have HCl plus pyridine, again it will go through Markovnikov. The anti-Markovnikov rule will be only applied if you have HBr with pyridine. So mark it somewhere. If you have HBr plus pyridine with alkenes, then anti-Markovnikov. For other cases, for example, simple HBr, simple HCl, or simple HBr, or sorry, simple HCl with pyridine, this will again go with Markovnikov. The only case where you will use anti-Markovnikov approach is when HBr is present in pyridine or ROR. Is this clear?
Yes, sir.
I have written it in Urdu as well. HBr के साथ pyridine use करते हैं, HCl के साथ नहीं. Right? Okay.
Sir.
Now, if you have alkene and you have Br2 in presence of CCl4, this is again important. If you have a case like this, you will again do what? CCl4 is what? CCl4 is a non-polar solvent. And here CS2 was also non-polar solvent. So we will, similar to the previous case, we will add our halogen across the double bond, right? Simple double bond के across addition. Okay.
Sir.
Right. See, next is Finkelstein reaction. This is again important because it is a name reaction. What we are doing here, from alkyl halide or alkyl bromide, either RCl or RBr, you are going to convert it into Ri, alkyl iodide, right? Finkelstein reaction is used to prepare specific haloalkane, which is alkyl iodide. Okay. For this reaction, what we are doing is basically we are reacting Rx, which is haloalkane, with NaI, which is sodium iodide, in presence of dry acetone. This is important, right? If you are doing this, you are getting Ri and NX. What is this NX? This could be NaCl or NaBr depending on the starting reagent. If you have RCl here, you will get NaCl. If you have RBr, you will get NaBr. Now, the important thing about this is the side product is going to get precipitated, right? This will precipitate, and due to this, it will facilitates the forward reaction as per Le-Chatelet principle. Why? Try to understand. See, you have a beaker. Okay, you have what? A beaker. You have sodium iodide, or they can give you Ki as well, potassium iodide. Okay,
Sir.
so sodium iodide or potassium iodide are dissolvable in dry acetone. So if I have, suppose this is dry acetone and this is my Ki. Ki will dissolve in this medium into K positive and I negative. Okay.
Sir.
Now, because this is in the form of ions, this I negative will do what? This I negative will attack here and this like displace this X. Okay. And
Sir.
the product, this NaX, this NaCl or NaBr is not soluble in our acetone. And they will do what? They will not get dissolved. They will simply do what? They will precipitate out at the bottom. This is NaCl or NaBr. Okay,
Yes. Yes.
that's with the help of this, you can simply like discard it and you will get your forward reaction. More and more product. Okay, Lee-Chatley principle is validated. Is this clear?
Yes, sir.
Now, the last, the last reaction of our haloalkane is Schwarz reaction. In Finkelstein reaction, we tried to made a specific haloalkane which was alkyl iodide. In Schwarz reaction, we are going to prepare alkyl fluorides. The synthesis of alkyl fluorides are best accomplished by heating on alkyl chloride and bromide in the presence of metallic chloride. Again, you will use the starting reagent as alkyl chloride or bromide. You will react them with metallic chlorides. Why you are doing this? Why a specific reaction? Why a specific name reaction is needed for the preparation of alkyl fluorides? Because fluorine is very reactive. Okay, a controlled reaction with fluorine is very difficult. So due to that, we need a specific name reaction, which is Schwarz reaction, where we are doing RCl or RBr, reacting it with metal fluorides. It could be AgF, it could be Hg2F2. We are heating it and getting our desired product. This is making sense.
Sir.
So that was about our haloalkane. Try to go through this and please ask me any topic if you have a doubt. I have shown here, like this NaCl is dissolvable in dry acetone. It is dissociated basically in I negative and Na positive. This I negative can travel in that liquid medium, and this I negative will go to R and displace the X and get attached there, right? And this X will
Yes, sir.
then form a bond with Na, and NaCl or NaBr will be precipitated out. Okay, just
Yes,
give
sir.
me a second. You can use Ki as well, okay? Now, please go through this, and if you have any doubt, please ask. Then we'll go to the next topic. Are you reading?
Sir.
Okay. These are like 10 to 12 pages notes. And if you somehow able to like memorize it, then you will be able to do most of the question of your exam, right? But the thing is, to understand it, you have to get the approach, like how the things are working. For that, we have to talk about it in bit depth.
Then, sir.
Right. Try to look at this as well. I missed one thing. We did not talk about alkynes, right? See, if you are having alkynes as your starting reagent, then you will use 2 moles of HBr, simple. Suppose you are doing this, then what will happen is it will form a bond like this, okay?
Yes, sir.
If you have somehow added pyridine, then this will go like this. Okay, same.
Sir.
You have to just use 2 equivalents instead of one, right? This Finkelstein is important. Try to like They might ask you directly what is Finkelstein, so try to understand it. Okay? Finkelstein, Schwarz, Darson, these are the important reactions. And this haloalkane, this alkene one as well. Shall we move ahead?
Uh, in
Ask.
Schwarz reaction, we will not have any precipitate, right?
In fourth
Schwarz
reaction,
reaction. No
so
Schwarz
okay,
reaction.
Schwarz, no precipitation. In
Yes.
Schwarz, you will have no precipitation, but in Finkelstein, you will have precipitation because our this NaI is having a bit of ionic character, more ionic character. Have you heard about Fezan's rule? That like distortion due to the big size of cation and small size of anion. Have you heard about Fezan's rule?
So,
Huh. So in NaI, our cation is small and anion is very huge, right? So the distortion is
yes.
more, the polarization is more. Due to this more polarization, it is dissolvable in our dry acetone. But as we are moving with the small anions like chlorine and bromine, we are seeing less polarization, right? Due to this less polarization, they are not dissolvable. We like for now, you can just try to learn it. I will show you like some animations as well to like imagine it now, how the things are happening. So for now, just
So,
remember it. We will talk about it in detail. This is done.
sir.
Okay. Now we will try to make what? Aryl halide. Aryl halide. Okay.
Sir.
What are aryl halides? Aryl halides are those species where the halogen is attached to a benzene kind of structure. Benzene type of ring. Okay.
Sir.
Now, mm, see again, the first step is going to be what? To prepare what? Prepare haloarenes. We have to first try to make like understand a method with the help of which we can prepare this haloarenes. So for the first method is what? Suppose you might have this toluene, or you can simply use benzene as well. If you are using simple benzene without the CH3 group, you will observe the same reaction. But if you are attaching this CH3, this benzene ring is doing what? It is becoming more electron rich because this benzene, sorry, this CH3 group is donating electron density, right? By plus I and
Yes,
plus
sir.
H. So if in question in your exam, they are not giving this toluene, so don't get like panic. You just simply have to apply the same approach. Okay. Now, one thing that we need to understand here is suppose if I am not using this, if I am just trying to proceed the reaction with X2, if I am just trying to proceed the reaction with what? Only Cl2 or let it Br2. Okay. I am not
Yes, sir.
using any catalyst. So this reaction won't occur. Why? Because our benzene is a very stable species. It is aromatic compound, right? If something is stable, then why it would want to react with something else, right? So if I am seeing this Cl2 or Br2 as an individual, as a simple, as an individual species, they are not electron deficient enough. They are not strong enough to attack at a compound which is very stable. So our first step is going to be what? We will make this Cl2
Catalyst.
or Br2 into a strong what we call that electrophile with the help of our Lewis acid or catalyst, right? So I will use AlCl3 or FeCl3 with my Cl2 or Br2. What it will do here is this. This is Cl2. This will react with this AlCl3. It will donate its own electron. And what I told you in the like a few minutes back, if something is donating its own electron, it will bear a positive charge like this.
Sir.
Chlorine is a very electronegative species. It will get very angry and like it will try to neutralize this charge. So what it will do? It will basically take the electron from the next chlorine and convert into this. And now in my solvent, in my container, I have a electrophile which is very strong. Cl positive is a very strong electrophile, right? Now, this Cl positive, after reacting all this, what I got? Cl positive, and this Cl positive is attacking. The attacking party is Cl positive, and it will attack at the para position and ortho position, and it will make what? Para and ortho isomer. Okay.
Sir.
Why it is attacking at the para and ortho position only? Because due to resonance, the negative charge or positive charge only revolve at ortho and para position, and due to which the para and ortho positions are having a negative charge due to resonance, and those two sites are comparatively more electron rich if you compare it with meta, and that's why our electropositive thing, which is electrophile, will try to attack at a site which is more electronegative, because the more the negative charge, the more will be attracted the electrophile. Okay, is it making sense?
Sir.
I hope it
So due
is.
to resonance, only at the ortho and parapod.
Yes. See, if I'm doing resonance now, the negative charge will revolve. Both the negative as well as positive charge will only revolve at either ortho position or para position. So the charge density is comparatively more at these sites. So if I am a electrophile, if I am someone very poor, right, I will try to go someplace where there is very much amount of money, right? Very like so much money, right? I will try to go there. And if I have a
Yes, sir.
place, if I have a if I have to choose out of meta or ortho para, I will definitely choose meta, oh sorry, para or ortho, because it has more electron density. They can offer me more help, right?
Sir.
So para isomer is usually the major isomer, right? If they ask you which
Yes, sir.
isomer is major, so you will for now choose para, right? I showed here as well. Like this is ortho position, the charge is revolving here only, right? See,
Yes, sir.
it is a electrophilic substitution, right? Electrophile is attacking. So electrophile is going at the ortho and para position. Suppose it was a nucleophilic substitution. Suppose it was a nucleophile. There was a nucleophile which has to attack. So where the nucleophile will attack? Nucleophile will try to find a site which is less electronegative, right?
Yes,
A
sir.
place which is not that rich. So if we are using a nucleophile, then nucleophile will attack at the meta position, and the electrophile will attack at the para position. Okay.
Yes, sir.
Now again, very important reaction. Send me a reaction. Just give me a second. Give me 2 minutes. Meanwhile, try to read what is written, right? When a primary aromatic part, try to read this. Okay, have you read it?
Sir.
See, this is a very important reaction. So what we are doing here is we are starting with aniline. This is aniline, benzene with the NH2 group, and we are reacting it with NaNO2 plus HCl. X could be Cl, Br, right? Or you can simply say HNO2. Why? Because after these two reagents react, they will provide HNO2 itself. So you can either write HNO2 or NaNO2 plus HCl. We will go into the mechanism as well after exam. So for now, try to understand it. You will start with aniline. You will react it with NaNO2 plus HX or HNO2, right? Then you will get this benzene diazonium salt, a very important intermediate, right? Here it look like this: N positive, then triple bond, and then X negative, right?
Sir.
This is a benzene. See, now our main purpose is what? Our main purpose is to prepare haloarenes, right? A halogenated compound. So after this, you will react it with cuprous halide. You will react it with CuX, basically Cu2X. You can write, or you can write in NCRT. It is written as Cu2X2. So use it. If you use it, it is also correct. But to be like sure, use Cu2X2. This X could be what? Cl or
Yeah.
Br. Then you will get your halogenated compound, haloarene, and the N2 gas will be evaporated, right? Why this mechanism, this reaction is very important? Because similar to our Darson method here, the side product is what?
Nitrogen.
No, no, no. Or like in what form it is? Nitrogen is in what form?
Gas.
Gas. And gas will automatically will get evaporated and you will get your pure compound basically, right? So the
Yes, sir.
filtration part will be like can be avoided here, right? You
Yes,
can
sir.
prepare chlorobenzene or bromobenzene with the help of cuprous chloride, cuprous halide. But what if you need to prepare iodide, benzene iodide? So for benzene iodide, you will simply shake your solution in presence of Ki and you will get benzene iodide. So try to read it. Replacement of diazonium group with iodide does not require the presence of cuprous halide, and it is done by simply shaking diazonium salt with potassium iodide. Right. This reaction is very reactive that you don't need even cuprous chloride. You will just add Ki and you will get your product. Is it simple or do you have some
Yes, sir.
questions?
So,
The last method is from phenol. With the help of phenol, if you are adding phenol in the presence of, sorry, if you are adding PCl5 in the presence of phenol, you will get your haloarenes. These are the three methods to prepare haloarenes. Right. Okay.
yes, sir.
Now, we will talk about the reaction of haloarenes. Similarly, like this. Here, we did what? The first four ways were to prepare haloalkenes, right? In the fifth and sixth, we chemically reacted. The starting reagent is haloalkane itself, right? We
Yes,
started
sir.
with haloalkane. We reacted haloalkane with different stuff to get haloalkane again. So basically, in the fifth and sixth, these are the chemical reaction of haloalkenes, right? So in the
Yes, sir.
first four part, we try to make haloalkane, and from fifth and sixth, we try to react haloalkanes. Similarly, three methods were to prepare haloalkanes, haloarenes. Now we will talk about the reaction of haloarenes. How? You have prepared this haloarene. Now you will try to use this haloarene to prepare new compounds. So first of all, let us talk about the reactivity of haloarenes, right?
Yes, sir.
Aryl halides are extremely less reactive towards nucleophilic substitution reaction. Why? Try to understand it. What is a nucleophile? A electron-rich species, right? a
Sir.
species which is having an electron pair or lone pair to donate. It is an electron rich species basically. And what is a benzene? Benzene itself is electron rich. It is very stable compound, right?
Sir.
If I have a benzene which is electronegative, which is having electron density basically, and if I'm trying to add a nucleophile into it, then electronegative species, a negatively charged species, and a negatively charged species, they will try to repel each other. They will not try to like approach each other basically, right?
Sir.
So aryl halides, benzene derivatives of haloalkanes, sorry, halogenated benzenes are less reactive towards nucleophilic substitution because one you can like understand with that approach as well, and there are four specific reasons that you need to write if they ask you in your exam. The first reason is due to resonance. This this chlorine is doing resonance here, right?
Sir.
This is chlorobenzene or not?
Sir.
Chlorobenzene is a haloalkane, sorry, haloarenes, right?
Sir.
If I try to react this compound with a nucleophile, suppose I have a nucleophile and I'm trying to react it, this will not react. Why? Because this is doing resonance. It is transferring its own electron pair into the ring, right? It is pushing the electron density. It is making the benzene ring more electron rich. Due to the resonance, here we are observing what? Double bond character. This chlorine and carbon are having partial double bond character or not?
Yes, sir.
Now, if a nucleophile will try to attack, then it will see a double bond basically. Which bond is easier to break, a double bond or a single bond?
Single bond.
Which one?
Single bond.
Single bond, right? So, because of partial double bond character in haloarenes, it is very difficult to break it. So, the nucleophilic reaction won't proceed. So, try to read this one out. CCl bond acquire a partial double bond character due to resonance. Bond cleavage in haloarenes are difficult than haloalkanes. They are less reactive toward nucleophilic substitution. Is the first reason understandable?
Yes, sir.
For the second reason, in haloarenes, this carbon is sp2 hybridized. And for haloalkanes, where you were doing the nucleophilic substitutions, this carbon was sp3 hybridized, right?
Yes, sir.
The second reason is due to hybridization. In haloarenes, we have sp2 hybrid carbon, and in haloalkanes, we had sp3. And if we are having sp2, then those are electron negative. Like sp2 carbon is more electronegative. If I am more electronegative, I will try to uh, like bring my side groups closer to me. So in haloalkenes, the bond length is 169 picometer. But for haloalkane, the bond length is a big, like larger. So if I have a shorter bond, right, and a longer bond, which bond is easier to break? Longer bond, right?
Longer bond.
So this
Yes,
is
sir.
another reason. sp2, because here we have sp2, here we have sp3, right? Instability of phenyl cation. Suppose we might go like this. For example, this is my chlorobenzene, okay? What I will try to do? I will do the self-ionization. Let us go by SN1 mechanism. What's the first step for SN1 mechanism? Self-ionization. Then I will, if I remove the Cl, then I will get this. This chlorine will get these two electron and I will get a phenol cation type of structure, right?
Yes, sir.
This is very, very unstable. If this is unstable, what I told you in the early classes, if something is unstable, it will not exist for like for long period of time, right? It will just appear and disappear. If we have to attack, if a nucleophile has to attack somewhere, that site needs to exist for some time, right? So that the
Yes, sir.
nucleophile can observe it and come closer to it and attack the party, right? If the site is just appearing and suddenly disappearing due to instability, then the nucleophile won't be able to attack it, right?
Yes, sir.
So if we are going with phenol cation, it is very unstable, it won't exist. And what is a phenol cation? This benzene with a positive charge. So try to read this one out as well. Phenol cation formed by self-ionization will not be stabilized by resonance. That means SN1 ruled out. SN1 reaction won't be happening here. And as well as no backside attack inversion will like SN2 will rule out as well. Right? You can write it. SN1 not applicable as well as SN2 not applicable. Right? The last reason is the one which we discussed at the starting. Because of possible repulsion, less likely for the electron-rich nucleus to approach the electron-rich arenes. If two parties, both of them are rich, right? If both of the parties are rich in terms of chemical reactions, they won't approach each other. In normal human world, right? Only rich people attract other rich people, right? But in
Yes, sir.
chemical reaction at atomic level, if two parties are rich, they will try to repel themselves, right? So at chemical
Sir.
level, things are okay. This was the mechanism of that Senmay reaction. For now, I won't suggest you to go into this because they won't ask you the mechanism. The mechanism we will do because we need to understand organic chemistry, right? We need to do the further chapters as well because if we don't do the mechanism part, we won't be understanding anything. So for now, you can skip it. This one you should remember. This benzene diazonium salt, which we prepared in the what? Senmay reaction.
Sandmares.
This is a very, very important intermediate. Suppose H3. See, suppose I'm doing an experiment in my lab, right? I still use this reaction. I still use this reaction in my lab. Suppose I have to make phenol, right? I have to make
Sir.
phenol. So what I will do? I will take aniline. I will react it with our NaNO2 plus HCl. Basically, send my reaction, and I will get what? This benzene diazonium salt. The moment I get the benzene diazonium salt, I can prepare several compounds. So many compounds basically. If I react with Cu plus chloride, CO2, X2, I will get what? Halogenated benzene. If I react with KCl, I will get cyanobenzene. If I react with H2O, I will get phenol. If I react with H3PO4, I will get again benzene. So with the help of this benzene diazonium salt, you can get so many products, right? So this is a very important intermediate. This is not just limited to our haloalkane. You can form several compounds, right?
Sir.
Okay. Now, so far, what we tried to understand, if you have a nucleophile and you are trying to attack the nucleophile to a benzene or a haloarene, right? The reaction is less likely to go forward. The reaction is less likely to be feasible, right? We can say that.
Yes, sir.
So, suppose you are saying, I don't know, I have to do this reaction. No matter what the cost is, I have to do this reaction. So, what you will do? In chemical reaction, what is the cost? Basically, if you apply more temperature or pressure, right? Basically, if you are in human world, what we say, if I give more money, the chances of my work to like get done is more, right? If you are giving someone more money, he will do your work like a bit faster, basically. You can say that.
Sir.
So in chemistry term, the money is basically heat or temperature, heat or pressure. So under normal condition, this reaction will not go forward, right? Because
Yes,
a
sir.
nucleophile will not attack at a electron-rich species. The reasons are that we have discussed, the four reasons, right? But
Yes, sir.
But if you have given a very high temperature, high pressure, then this reaction can occur. The reaction can give you a product. So what you will do? This is called what? Dawes reaction as well. You might have heard this in your class if they have completed this chapter. No? Have you heard about this Dawes reaction?
Yes, sir.
So what is happening? Ideally, the reaction won't go. But if you are giving it very high pressure and temperature, the reaction will proceed. How the reaction will proceed? First, it will create a phenoxide ion. Why? For now, you can take it as in presence of base. NaOH is base or not?
Sir, it is a base.
In presence of base, we cannot form a acid. So to form a like acidic compound, a base like phenol is acidic. So the last step is we need to like give it a acidic environment. Basically, we have to provide it at positive. So first step is NaOH, high temperature, high pressure, followed by acidic workup or H positive you can add. Okay. So this is what Dawes process. Now the thing that we need to understand. Suppose if I am applying a electron withdrawing group, what is the work of electron withdrawing group? What electron withdrawing group do?
They will withdraw the electrons present.
Electron density, good, good. What was the issue? Why the haloarenes were not reacting? What was the issue?
They
Because
had lots of electrons.
electron density. But if I
Yes,
have
sir.
attached a withdrawing group, what is this electron withdrawing group doing? Basically pulling the electron density from the benzene, right?
Yes, sir.
Basically making the benzene ring a bit poor, electron poor, right?
Yes,
So
sir.
what I am observing here is if I have added one electron withdrawing group, what I observed, the temperature condition dropped. Without electron withdrawing group, I needed 623 Kelvin temperature, but after introducing an electron withdrawing group, what I am observing, the temperature condition has dropped, right?
Yes, sir.
Now, if I have added two electron withdrawing groups, what are these two electron withdrawing group doing basically? They are pulling the electron density. They are basically making our benzene poor. Now, if our benzene is poor, if the benzene is having less electron density, now it will try to allow the nucleophile which is having electrons to attack itself, right? Because it is poor now, right?
Yes, sir.
So now what I observed, if I have applied two electron withdrawing group, the temperature condition drop down even more, right?
Yes, sir.
What if I have added three electron withdrawing group? If I have added three electron withdrawing group, I don't need to like apply the heat itself. Like the reaction will occur even at the normal condition. If you just warm your reaction mixture, you will get your product. Why this is happening? The reason for this is basically the issue was benzene was rich. Benzene was rich. Benzene was arrogant. He was not allowing the another person who was also rich to come close to itself. But what we did, we tried to introduce some electron withdrawing group. They made benzene poor. Now benzene is poor. The arrogance is gone. Now he will allow the nucleophile to attack itself. The more number of electron withdrawing group we attach, the more poor the benzene will become, and the more frequently or more like what word we should use, more prone it will be to the attack for the our external nucleophile. Is it making sense?
Sir.
Are you sure? If you have doubts, please ask me.
Sir, clear.
Okay. So what I have written over here is try to spell it out for me.
Sir,
This
the reaction,
no this part, the EWG present at the bracket one, that the
the
sentence I have written.
the EWG present at ortho and para position
Mhm.
activates the. So what is that? Activates the.
See, that thing is a nucleophilic substitution reaction. This is the short form. You in chemistry we write what is this? SNAR. SNAR means AR means aromatic, right?
Sir.
AR means aromatic, S mean substitution, N mean nucleophilic. So in short, we call it nucleophilic aromatic substitution. If we go by the name, we are using a nucleophile which is attacking at an aromatic ring and substituting some other group, right?
Yes, sir.
So
Yes,
it
sir.
is aromatic nucleophilic substitution. Why we are introducing at ortho and para position only? Why we are not introducing at para position? Sorry, meta position. Meta position.
Sir, because in ortho and para position, it is more electronegative. So
Yes,
electron
because
electron groups can.
good. So because meta position is not observing any kind of charge, and the extra charge is only revolving around ortho and para. And the moment the negative charge is coming at the ortho or para position, our electron withdrawing group is extracting it, right?
Yes,
Uh,
sir.
like stopping our benzene to be electron rich. Okay, I hope it is clear.
Yes, sir.
This is called Dawes reaction, Dawes process. Now, we talked about what? Nucleophilic substitution. Okay. Now we will talk about electrophilic substitution. Now the attacking party is going to be what? An electrophile, right?
Yes, sir.
Now we have basically two or like basically I guess four types of reaction. So the first one is halogenation. We already talked about this. If I only have Cl2, this reaction will not occur. Why? Because this chlorine itself is not very strong electrophile. After it react with our Lewis acid or catalyst, this is Lewis acid, or you can call it Lewis catalyst. This will become into Cl positive, and now this Cl positive is strong enough. This is poor enough to bag. Suppose you can understand it like that. This person is poor, but not that poor. So he will try to avoid begging. Okay. He will not like lay hands in front of people to ask money, right? What we are
Sir.
doing, we are converting it into a very like uh what we can say like we have a very we are giving it very extreme condition, like we are converting into a very poor person, right? We are converting it into Cl positive. Now it will try to do anything. It will beg. It will try to uh do theft, right? It will try to remove, like basically try to gain electron. So after converting into Cl positive, by reacting it with this Cl positive will attack at the para and ortho position and give us products. Is it clear?
Yes, sir.
See this thing. This will attack here, right? This will convert into Cl positive. This Cl positive is the party which is attacking at the ortho position and at the para position, right?
Yes, sir.
I hope this is clear.
Yes, sir.
And here, what is attacking an electrophile? So
Yes,
we
sir.
call this electrophilic aromatic substitution. The major product is para, the minor product is
Or,
ortho.
or-
The second is nitration, very important. What is happening here is basically these HNO3 and H2SO4 are reacting with each other and giving us NO2 positive. This NO2 positive is the actual electrophile. We have added HNO3 and concentrated H2SO4 in order to produce this compound, this reagent. This is the electrophile, the actual electrophile which is attacking. And this will attack where? At the ortho position
para position.
and basically nitration means addition of NO2. So we will show this. Is this clear?
Yes, sir.
We have to go into the mechanism as well. For now, I am just giving you like very brief about it, right? So
Yes,
that you
sir.
can go through your exam. What is sulfonation? The sulfonation is basically the addition of SO3H. Same at para and ortho position. What is the difference between nitration and sulfation? Sulfonation. In nitration, we are using HNO3 plus concentrated HOSO4. Okay.
Yes, sir.
But in sulfonation, we will only use what?
Heat.
No, no, no. Only concentrated H2SO4,
H2SO4.
not HNO3. Okay. This is the
Yes,
difference.
sir.
Right.
Yes, sir.
This is basically DAW's process. The side product is NaCl. I hope you are able to understand why NaCl, right? Because
Yes,
Cl
sir.
will move and Na will react. So the side product is going to be NaCl. Right. Give me 2 minutes, right? Let me just get some water. We have to discuss your test as well, right?
Yes, sir.
Yes. So what we will do tomorrow? I will wrap it up here, right? I will
Sir.
try to wrap it up here. We will discuss this leaving group, the solvent effect in the next class. And please try to bring doubts in the next class, okay?
Yes,
From the
sir.
previous chapters and from this chapter as well. Whatever, no
Yes,
matter
sir.
how small your doubt is, you can bring it here so that you can perform well in your exam. Just give me two
Yes, sir.
minutes. We will try to complete our today's agenda and we will discuss your test. Let me get some water. This is not going like all of this is not going through over your head, right? Some like you are able to understand some things, right?
Sir, sir, I'm able to understand almost all.
Oh, that's great, right? But if like in exam now you will see in exam they won't ask you directly these questions. Like if you have this, what you will get? They will ask you different question. They will give you a reagent, starting reagent, and they will tell you try to convert this from the end product, or they will give you some intermediates. They will ask you about the stability, or they will ask you like which is better SN, which substrate is going to show better SN1 or SN2 reaction, right? So
Yes, sir.
the exam for organic, I won't say like once we are done with this chapter now, once we are done with this chapter in detail, the next three chapter will be a child's play for you because the main thing, the mechanism part, the part where people used to like find themselves not understanding the concept, right? We will be able to understand them very well because I will explain you everything in very detail. So for organic, just try to revise
Yes, sir.
side by side. Otherwise, like I can teach you physical from the scratch. It will take like 1 or 2 days, but for organic, no one is like, to be very honest, to understand organic, you have to connect everything. Okay. All right. Now, see, let me do one thing to reduce the page number. Uh, right. Let me remove this page. Hmm. See, this nature of CX bond, we have already discussed it in depth, right? We have also talked about the exception. They might ask you this question: why the CHCl3 bond, the CHCl3 is more polar or having more dipole moment than CH3's F. Like the trend suggests something else. Why this is happening? Because the Cl is the ClC bond is exceptionally long. I told you about this, right?
Yes, sir.
About this exception. Now, Friedel-Crafts reaction. The Friedel was the name of the scientist. He made like processes or chemical reaction with the help of which we can add a alkyl group or acyl group. So for the first thing we are going to talk about is what?
Alkyl.
Alkylation. What is alkyl? Alkyl group is simple saturated compounds, like simple saturated hydrocarbons, or not?
Yes, sir.
This CH3, C2H4, C2H5, methane, ethane are basically what? Alkyl. So the addition of alkyl group to our haloarenes is called alkylation. Why we are adding uh, only to the haloarenes? Because the name of the chapter is haloalkenes. Okay. In the next chapters, in the next three chapters, these nitration, sulfonation, alkylation, chlorination, all of the reaction are going to repeat. Okay. The thing that is going
Sir.
to change is the starting reagent. Here, what we are doing is we are reacting our compound that we prepared. We tried to prepare our haloarenes with three methods. Now we have our haloarenes. We are trying to react it further to get further new compounds. Okay.
Yes, sir.
So if you have CH3Cl or you have CH3CH2Cl in presence of anhydrous AlCl3, it works as a catalyst. This alkyl part, this alkyl part will be attached to ortho and para position. Okay, simple as that. For example, if you have this one, okay, this Cl is attached here, CH2, CH3, okay, this ortho plus
Para.
Cl, CH2, CH3. Basically, para product and ortho product. The alkyl part will be attached towards the ring, and the Cl will be eliminated in the form of what? HCl. How? See, here we have a carbon or not?
Yes, sir.
We don't show carbon, but it is here, right? So this carbon, this CH3 will like this CH3 will come here. This will remove this hydrogen and get itself attached here. So H plus Cl will combine and give us HCl as a side product, right?
Yes, sir.
This is what Friedel-Crafts
Alkylation.
alkylation basically suggests addition of alkyl chain. Now acylation. See, this is acid chloride and this part is acyl part, right? Addition of this part is what? Acylation. Friedel-Crafts
Acylation.
acylation at ortho and para position. For example, if I am having this C2H5 C double bond O Cl. If I add this part at ortho and para position, then it will be called acylation as well. Different groups can be attached. You can use propane chain as well. Okay. You can use isopropyl chain. You can use tertiary butyl chain. But the condition is it should look like this. It should have a carbonyl compound, carbonyl group, basically C double bond O attached with the alkyl chain. This is acylation, right?
Yes, sir.
The important thing is anhydrous AlCl3. Without this, the reaction won't go forward. Why? Because this anhydrous AlCl3 is converting our compound into basically an electrophile. CH3 plus. CH3 plus we get after this. Should I show you? CH3Cl, right? AlCl3. Similar to the Cl2 part, this will attack. And if it is donating its own electron, then it will be a positive charge, right?
Yes, sir.
The moment it gets a positive charge, it will try to abstract electrons from its neighbor. It will get the electrons and generate what? CH3 positive and AlCl4 negative.
AlCl3
Similar
negative.
AlCl4 negative, right? And the party that is attacking in actual, right? After mixing these two stuff, we get this and this is the person, this is the substance which is attacking at the orphan collaboration. Okay,
Sir.
is it clear?
Sir.
Uh, please try to note this down, right? How the like CSCLC is attacking to ALCLC and how this is the actual electrophile.
Yes, sir.
Okay, I hope this is clear. Let us talk about the next. The last two reactions, right? The last two reactions are Wurtz fitting reaction, Wurtz reaction, and fitting reaction. Very, very simple reaction. See, when you have to make a alkane, right? What? An alkane, a simple alkane with a haloalkane. If you have a haloalkane and you want to get a alkane, then you will use Wurtz reaction. What you are doing basically? Try to read this out. When alkyl halides react with, try to read this out. This is very simple. It will take like 2 or 3 minutes. No, let me know once you're done.
Sir.
So first one is Wurtz reaction. Okay,
Yes, sir.
you will have a haloalkane because right now we are talking about the reaction of haloalkanes. Okay,
Yes, sir.
and you will have a sodium. So the thing about this reaction is you will use two equivalent of sodium and two equivalent of alkyl halide, and you will do what? You will write it like this, right? You will eliminate two equivalent of what? NaCl in presence of dry ether, and you will get CHCH3 plus 2 NaCl. This is what? Wurtz reaction. In Wurtz reaction, what you are doing basically, or you can write it like this:
We are
CHCl3
separating
plus 2Na.
haloalkenes from
No, no,
two
not separating.
alkanes.
See, you are converting a haloalkane into alkane, a simple alkane, right?
Yes, sir.
Now, in exam, if they say, if they give you a question, like if they give you this methane, right? If they give you methane, right? And they ask you to convert it into ethane, how will you do this? First of all, the moment you are required to make a chain like double. Suppose you are starting with one carbon chain and you are asked in question to double it, or you are starting with a two carbon chain and in question they are asking you to make a four carbon chain. Basically, they are asking you to double it. The questions where they are asking you to double the chain, you should always try to think about the Wurtz reaction, because in Wurtz reaction, what we are doing basically with from a
Doubling.
single carbon chain, we are making a double, right?
Sir.
Now, what we will do? First of all, I know there is something called Wurtz reaction, but for Wurtz reaction, the starting reagent is what?
Well,
It
sir.
is, it is not alkane. It is haloalkane.
Yes, sir.
Now, do I know some methods with the help of which I can convert alkane into haloalkane? I know, right? I
Sir.
will, in the presence of sunlight, I will react it with Cl2. Then I will get
Yes, sir.
CH3Cl. Okay.
Yes, sir.
Now, with the help of this, I can do what? Wurtz reaction. I will get 2Na and I will get to this and I will get my product. right? First step was
Yes,
to
sir.
convert it into haloalkane, then we will do simple Wurtz reaction. Here what we can do is, again, in the presence of Cl2, I will put it in sunlight. Okay. Now I will do the simple Wurtz reaction and get my product. They will ask you these kind of questions, right?
Yes, sir.
Please note it down. I am going to erase it. Make rough note or try to do the NCERT question. Is it a?
Sir.
So we talked about Wurtz reaction. Now we will talk about Wurtz fitting reaction. In Wurtz fitting reaction, what we are going to do is we are going to use a haloalkane. The condition is again same to Na, but we are using one haloalkane and one haloarene. The thing is same. We are going to eliminate what? NaCl and connecting these two things. In presence of what? Right. Right. Is it making
Yes,
sense?
sir.
This is what? Wurtz fitting reaction. Wurtz means alkyl haloalkane chain. Fitting means haloarene chains. If I am saying Wurtz fitting, one haloalkane and one haloarene. But if I am just saying fitting reaction, what should be the case?
Haloarenes.
Only haloarenes. Both are going to be haloarenes. Right. Again, this will eliminate, and I will get biphenyl. What is biphenyl? Two benzene ring joined together. Right. This was all
Yes, sir.
about your reaction and preparation part. Right.
Yes, sir.
In the next class, that mean tomorrow, I will go through, I will like we'll go through the physical properties, and I think we have talked about some of this. Have we talked about like the melting point, symmetry and stuff? I think no, right?